and thank you for giving me the chance today to present some of my results, which is about self-powered broadband hybrid organic inorganic photodetectors based on P.PSS and silicon micro-nanostructures. First of all, I would like to know first about photodetectors, which is the devices which convert the optical signal to electrical one. And there are many applications like optical communications, biomedicine, video imaging, and gas sensing. Depending on the electromagnetic spectrum, there are selective photodetectors which work in a narrow region of the electromagnetic spectrum, and there is broadband photodetectors which work in a wide region of the electromagnetic spectrum. So there are several photoactive materials, and silicon goes at the top of these materials, but due to the indirect band gap of silicon, most of the researchers try to improve the optical performance of silicon by applying a nanostructure material or hybrid nanostructures on the surface of silicon substrate. So today I will show some results about modifying the structure of silicon by applying porous silicon on the surface of silicon. Porous silicon is like a network of nanometer-sized silicon regions surrounded by void space, like this scanning image. So the optical properties of porous silicon is completely different from crystalline silicon, where it is like void spaces between the nanocrystals. So the morphology of porous silicon is like nanocrystalline silicon surrounded by amorphous silicon and silicon dioxide at the outer part. So how to fabricate porous silicon? Maybe it could be chemically or electrochemical process. So for the electrochemical process, it could be in hydrofluoric acid. So under specific conditions, we can get microporous, mesoporous, and macroporous, depending on the fabrication parameters like the type of silicon substrate and resistivity, formation method, if it is chemical or electrochemical fabrication method, and the concentration of the component of the solution, etching time, and current density in the case of electrochemical etching process, and illumination and temperature. So at that work, we will present the optoelectronic performance of 3 different configurations of photodetectors. The first one is based on silicon, which will work as the active layer, and P.PSS is the organic material, which work at the same time as anti-reflective coating, transparent conductor, and whole transport layer. In the 3 cases, aluminum is the bottom contact and gold is the top contact. So the modification of the active layer to be instead of crystalline silicon, we will modify the surface of silicon by applying or fabrication of nanostructured porous silicon. And the second modification will be instead of applying porous silicon on the whole surface of silicon substrate to perform microarrays of silicon to improving the optical properties by porous silicon and the electrical conduction by silicon arrays. To fabricate porous silicon is by electrochemical etching process, but fabrication of silicon and nano porous silicon microarrays will be in 2 steps. The first step is by photolithography, where the silicon substrate will spin coated by photoresist, then through a photomask in the form of square arrays and exposure to UV radiation, we can get micro arrays of square holes of silicon. And before etching of the photoresist, the sample was subjected to hydrofluoric acid to etch the square areas of silicon substrate. So the result after etching of the photoresist, we can get microarrays of silicon nanostructure inside the whole structure of silicon substrate. The morphology of the fabricated structures is like P dot on the surface of silicon substrate or on the surface of porous silicon and on the surface of microarrays of nanostructured porous silicon. And this image shows the morphology or the cross-sectional view of porous silicon layer, P dot layer, and the gold contact. And here, different magnifications of the microarrays of nanostructure porous silicon to show the dimensions and the morphology of the fabricated porous structure. The purpose of the fabricated microarrays of nanostructure porous silicon is to enhance optical properties and at the same time to enhance the electrical conduction of porous silicon. So from the optical point of view, by measuring the reflectance of nanostructure porous silicon, we can see that the optical reflectance greatly decrease. However, by the composite of porous silicon and silicon, we can see that the difference between the reflectance with silicon is more or less closer. But after the addition of the anti-reflective coating of P.PSS, we can see here that the difference between the reflectance of silicon plus P.PSS and the microarrays of nanostructure porous silicon is greatly improved. So from the electrical point of view, we can see here that the electrical conduction of the composite between silicon and nanostructure porous silicon is more or less closer to the values for crystalline silicon. So this is for the electrical conduction of the whole device. And to study the electrical conduction between the interfaces of the optoelectronic device, we used Nyquist plots by electrochemical impedance spectroscopy. And by fitting the data between the imaginary part of impedance to the real part, we managed to fit it to the equivalent circuit model. So the first structure was modeled to this model, and the third structure, which modified by nanostructure porous silicon and silicon, was modeled to this model. From the electrical parameters, we can see here that the electrical conduction by the hybrid nanostructure between silicon and nanostructure porous silicon show better data or better electrical conduction than the one which based on porous silicon. And then after studying the optical and the electrical properties of the three different structures of photodetectors, we studied the optoelectronic properties at zero biasing for the three structures in a wide range of incident powers from 100 microwatt to 1 milliwatt. So from the obtained results, we can see here that the three devices show a perfect performance as a photodetector, while the one which contains a microstructure of porous silicon give the best results. And this image shows the comparison at 30 milliwatt and zero biasing between the three structures. To understand the performance of the three structures, we studied the energy band diagrams. So for example, for the first configuration, which is P dot as the top layer and silicon as active layer, we can see here that the generation of electron hole pairs is due to the active layer is silicon, and as P dot is a hole transport layer, so under illumination, holes will go in this direction to the front contact, and electrons will go to the back contact, and then generation of electron hole pairs. And in the case of device which has nanostructure porous silicon, we can see here that the energy gap of nanostructure porous silicon increased due to the morphology of porous silicon, which composed of amorphous silicon and air. So each energy gap increase on silicon, and the same direction of holes will be to the front contact and electrons to the back contact. And for the third case, which composed between silicon and nanostructure porous silicon, we suppose that the two mechanisms will work at the same time because of the structure of the top active layer. And then for the relation between the photocurrent and time, the response time, we can see here at the wide range of incident power, the photodetectors work perfectly in the three cases, and the one which has the nanocomposite of nanostructure porous silicon and silicon shows the best rails, and the response to light is very fast. And for studying the relation between responsivity and instant power, responsivity is the relation between the photocurrent minus the direct current or the dark current, and the intensity of the incident power and the area of the active layer. So from the obtained data at zero biasing, we can see here that at low irradiation levels, the modified device show a better responsivity than the one which has just porous silicon layer. But at high irradiation levels, we can see here that the modified structure show the highest data. Also, to study the photo response or the photo current in relation with the incident power, you can see here that with increasing the incident power for the three devices, the photo current increase. The detectivity, which detects the response of the photodetector to the small signals of incident power, and we can see here for the modified device that the detectivity goes on the same manner as the responsivity. For the speed of the fabricated devices, we can see here that from the relation between the photocurrent at 50 Hertz, the response time of the device is very fast in the range of microseconds, which means that it could work for small signals and very fast. Finally, the spectral responsivity, which was measured with monochromatic light in a wide range of wavelengths from 300 nanometer to 1200 nanometer. So we can see here that the device, which is based on silicon, show a broadband optical photo response in a broad range of the electromagnetic spectrum, while the one which modified by nanostructure porous silicon on the whole surface of the active layer, we can see here that it shows just narrow band at around 1000 nanometer, which means that it could work as a narrow band photodetector in the near infrared region. While the device which was modified by combining between silicon and nanostructure porous silicon on the surface, we can see here that the photo response greatly improved by combining between the optical properties of porous silicon and the good electrical conduction by silicon. We can conclude here that we managed to fabricate fast response photodetectors that was self-powered with three different configurations. The first one was based on planar silicon, and the second one was based on silicon and porous silicon on the top surface to improve the optical absorption. And the third one to combine between improving the optical absorption and the electrical conduction. It was like microarrays of nanostructure porous silicon to improve the optical absorption, and in between is the silicon, which is heavily doped, so it could improve the electrical conduction. So from the obtained results, the relation between reflectance and wavelengths, we can see here that the device which combined between silicon and nanoporous silicon show intermediate values of reflectance. And for the electrical conduction from current voltage curve, we can see here that the electrical conduction of the modified structure is close to the one with silicon. However, with porous silicon, we can see here that the electrical conduction decreased. For the photo response, the photo current in relation with the volt, the open circuit voltage increase with the modified structure, with modifying the structure, for example, at 30 milliwatt. So we can see here that the photo current for the modified structure is higher than the one with porous silicon on the whole surface and higher than the one which is based on planar silicon. And this is the response with the incident power. So between lightning on and off, we can see here the response of the photodetectors, for example, for the modified one, and this one showing the values of responsivity in relation with the incident power for the three devices, and how the modified device can show the highest optical responsivity in the low irradiation levels and at high irradiation levels. And finally, the relation between responsivity and wavelengths, we can see the broadband optical photo response of the modified structure, however narrowband for the one which is based on just porous silicon on the surface. Thank you for your attention.